Now we'll talk about geometry of gradients. The geometry of gradients starts with the question, at a given point, here we are at a given point, and from this point we can go in any direction, and out of all these possible directions, which direction has the maximum rate of change of f? So which one leads to the fastest increase? Fastest rate of increase of f. Looking at these schematics, these are contour plots for functions. In the contour plot on both of these contour plots, it looks like there's a hill. It's getting taller as you approach the center of this hill, and so we want to go as steeply up as possible. So just from this point, what's the steepest up direction out of all possible directions from this point? And the blue arrows illustrate that. That's the direction we're looking for, the steepest up direction. If you started at point P and took the steepest each time, you would get to the top of the hill. It wouldn't necessarily be the shortest straight line distance, but it would be keeping things as steep as possible at each moment. How do we find those directions? How do we find the direction with the maximum rate of change? Well, the answer is that it's the gradient. The direction of the maximum rate of change is the gradient. It points uphill as much as possible. It's the steepest uphill pointing vector. We could ask the question why that is. Well, the rate of change in the direction u of function f at point P is the dot product gradient of f at point P dot product u. And that would be the magnitude of the gradient times the magnitude of u times the cosine of the angle between them. And what's the largest possible value for this? The largest possible value is to have the magnitude of the gradient times the magnitude of vector u, and that happens when cosine theta equals 1. So theta is 0, and the gradient and u, vector u, are parallel in the same direction. So to make this rate of change in direction u as large as possible, then the direction you want to go in is the same direction as the gradient. Here's a question for you. Here's a table that gives values of the function xy. These are the x coordinates, 4.95, 5.1, and the y coordinates, 2.93, 3.1. And then inside the table are the z values. These are the z values, and z equals f of xy, the function outputs. You're being asked to make an estimate for the vector, which is the gradient f of 5, 3. And then which quadrant does that gradient vector point into? Out of the 4 quadrants, which quadrant does the gradient vector at this point into? Okay, you can pause the video and think about it. The answer is that the gradient points into quadrant C. It points into quadrant C because remember the gradient points to the steepest uphill direction. This one to the northeast is actually downhill, and so is that one to the southeast. Those are downhill. Going to the northwest, there's some increase. That's pointing uphill. But going to the southwest, there's more increase. That's just being a larger number. And so that would be the steepest uphill direction for the gradient vector. And now, if you wanted to estimate the gradient vector, I won't go through the whole thing, but I'll show you how you could estimate the x component. The partial derivative with respect to x is approximately equal to f of 5.1 minus f of 5 divided by 0.1. So just looking at these two entries. So we have minus 0.7 divided by 0.1. So we would end up with minus 7. So the gradient of f should start with something like a minus 7 and then something that we haven't figured out. And I don't know if that's equal. Let's just say approximately equal. That's the estimate we got based on the slope between these 2 points, which is going to be pretty close to the tangent slope. I'll leave the y for you if you're curious.